So I'd call this the clever way to reduce this. If you can think of two factors of 24, where one of the factors is the largest perfect square that divides evenly into 24, that's the money way to reduce. This is the two-factor strategy. The prime factor strategy is maybe easier if you own my calculator. The prime factor way to reduce gives the same answer, but I don't have to be quite as clever. I'm going to do a prime factor tree for 24, and to do a prime factor tree, you just write a branch or an upside down V under the number and write any two numbers that multiply out to be 24. I could do 4 times 6, 3 times 8, 2 times 12. Let me do 2 times 12 just because I'm thinking of it. 2 is prime, so I circle it. 12 is not prime, so I branch it. 12, I know it's 2 times 6. I could have written 3 times 4. 2 is prime, so I circle it. 6 is not prime, so I branch it. 6 is 2 times 3. Both 2 and 3 are prime. So the prime factoring for 24 is 2 times 2 times 2 times 3. To reduce by prime factoring, every time you get a pair, you get one of these out front. So the 2 that goes in front of the square root is from the pair of 2's. And any non-pairs, these are leftovers, get multiplied. They're going to be singles here. You're going to multiply them and place under the radical. So this 2 and 3 that weren't part of the pairing of the 2's get multiplied and get thrown under the radical. Regardless, the square root of 24 reduces to 2 square root of 6. If you're clever, you can break it up this way, maybe even do that in your head. This is a little more than students can do as the numbers get bigger, it gets hard. This prime factoring is not so hard, especially if you own this calculator, because this calculator does prime factor trees. I'll show you that in a second. So for 19, if I want to reduce the square root of 54, I can look at all the perfect squares. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49. If I could find the biggest number in this list that divides evenly into 54, I can break 54 up into 2 square roots being multiplied. And I know that this is the only number in the list that 54 divided by it is not a fraction. So I'm going to break up 54, or the square root of 54, into the square root of 9 times the square root of 6. I'll do the square root of 9, and I'll leave the square root of 6 alone. On my calculator, square root 54 tells me it's 3 rad 6. That's just what I wrote down. This is the clever way, and it's the way that I generally do. If you're good with numbers, maybe you can do this. The non-clever way is the prime factor tree approach. If you own my calculator does prime factor trees. So rather than every time I'm stuck with a number that I want to do a prime factor tree for, rather than me having to every single time make a tree, I can I can use my technology to do the prime factor tree. So the prime factor tree for 54 is 2 times 3 times 3 times 3. I did it without explaining. And once I have a prime factor tree for a square root problem, anytime I get a pair, I get one of those out front, and anything that's left over that's not paired gets multiplied and goes back under. So this would be the way to show that this is going to be 3 times the square root of 6. I have a pair of 3's and a single 2 and a single 3 left over that get thrown under. So on my calculator, prime factor trees, to do prime factor trees, calculator prime factor trees, it's a big deal. It's going to save you so much time. And I'm not going to do prime factor trees by hand, assuming you can do them by hand if you don't own this calculator. First of all, I have to be in mode 1. So I'm just going to type mode in 1 just to make sure I'm in mode 1. I never have to do that again. If I want to do a prime factor tree for 54, I'm going to type the number 54 followed by the equal sign. And that's going to make 54 in the upper left and the bottom right hand corner. After I do that, I'm going to hit the shift key and this degrees, minutes, seconds, or quotes key, because above that key you can see the word FACT. So now I'm going to type shift and this degrees, minutes, second key, shift, degrees, minutes, second, and it tells me that 54 is 2 times 3 times 3 times 3. It says 54 equals 2 times 3 cubed. And that's 2 times 3 times 3 times 3. And I get the pair of 3s that go out front with 1 and the singles go under. Let me move down to do number 20. Number 20 wants me to reduce the square root of 106. This number is too big for me. To do the clever way. The clever way, I'd start looking at the perfect squares. I'd ask myself, are any of these perfect squares, if I divide them, 106 over them, if I don't get a fraction, then I would break it up into 2 radicals. So if I can search this list and find the biggest number that goes evenly into 106, I can break 106 up into a couple radicals. I don't care to do that because it's too big of a number for me. I'm going to do a prime factor tree for 106. By hand, I can go 106 is 2 times 53. They're both prime. On my calculator to do a prime factor tree, this is the only calculator I know that does prime factor trees. Most calculators don't. I type the number 106, follow it up by hitting the equals key, so the 106 is in the upper left and the bottom right hand corner. Then I hit the shift key, and then directly under the square root key, the degrees, minutes, seconds, or the quotes key. And it tells me 106 is 2 times 53. When I go to reduce the square root, anytime I get a pair, I get one of those out front. Anything that's not part of a pair gets multiplied and it stays under the radical. There aren't any pairs. This radical doesn't reduce. Both the 2 and the 53 are going to stay under the radical. So for an answer for problem 20, that radical is not a reducible radical because there aren't any pairs in its prime factoring, or none of these numbers divide evenly into 106. Had I just did this on my calculator, the square root of 106, my calculator is smart. It knows that that doesn't reduce. We're going to kick up the difficulty just a little bit. If there's a number in front of a square root, it doesn't impact me so much. That number is going to get multiplied by any number that I happen to bring out front. So for problem 22, for what it's worth, problem 21 is 2 times the square root of 63, just in case some glare is making this horrible. I need to reduce the square root of 98, and if I bring a number out front, I'm going to take that number and multiply it by the 3. I just like reducing with prime factor trees. I think it's easier to follow. You can reduce this by breaking it up into 2 radicals. I'll show you how that's done, but I'm going to do the prime factor tree. For me, it's easier to teach reducing by prime factor trees. So I'm going to do 98. 98 is even. It's 2 times 49. If I didn't know that, I'd just go 98 divided by 2. And that would give me the 49. 2 is prime. 49 isn't. 49 is 7 times 7. So the prime factoring for 98 is 2 times 7 times 7. On this calculator, to do that prime factor tree, I go 98 equals shift quotes key, and that gives me 2 times 7 squared, which is 2 times 7 times 7. The single 2 is going to remain under. The 7 is going to come out front, but I'm just going to get 1 out front, and it's going to get multiplied by the 3 that's already there. So the 3 that's already outside is going to stay outside. I'm going to bring a 7 out front, and I'm going to leave a 2 under. And for 22, my answer should be 21 square root of 2. If I was just entering this on my calculator, 3 times the square root of 98, it would tell me it's 21 square root of 2. If I wanted to do this the clever approach, the non-prime factor tree approach, would to say this is going to be 3 times the square root of 49 times the square root of 2. 49 is the biggest perfect square that divides evenly into 98. The square root of 49 would turn to 7. The 7, once it's removed from the square root, you could multiply. I can't multiply a number outside a square root by a number under a square root, because a square root is like a fraction exponent. That would be doing exponents before multiplications. So you should be able to do 21. My calculator chokes on cube roots. It gives decimals. I can't do the cube roots on my calculator. To reduce a cube root, I could either do it by prime factor trees or by the clever. The breaking it up into 2 radicals. If I want to solve this like I did breaking up the square roots with 2 radicals, I need to find the largest perfect cube that divides evenly into 24. So if I want to do the non-prime factor tree approach, I'm looking for the largest perfect cube that divides into 24. And my perfect cubes are 2 cubed is 8. That's a perfect cubed. 3 cubed is 27. 4 cubed is 64. 5 cubed is 125. If I could find the biggest number in this list that divides evenly into 24, I can break this into 2 pieces. The biggest perfect cube in this list that divides evenly into 24 is 8, because 24 divided by 8 is 3, or 8 times 3 is 24. I could reduce this by making it into the product of the cube root of 8 times the cube root of 3. The cube root of 8 is 2. The cube root of 3 is not reducible because there isn't a perfect cube that divides evenly into 3. That would be the strategy, breaking it up into 2 radicals. The prime factor tree approach is similar, but it's a little bit different. In a square root, the prime factor tree approach, every time you get 2, you get 1 out front. Not the case for cube roots. I'm going to do a by hand prime factor tree. 24 is 3 times 8. 8 is 2 times 4. 4 is 2 times 2. The prime factoring for 24 is 2 times 2 times 2 times 8. In a cube root, because the index is 3, each 3 of a kind, this should be a 3 over here, because it's 2 times 2 times 2 times 3. Every time you get a 3 of a kind equals 1 out front. And the leftovers get thrown under. So here I have a 3 of a kind, a 3 2s. I get 1 of those out front, and I have a leftover, it gets thrown under. Again, prime factor trees on this calculator, I just typed the number 24, it hit equals, shift in quotes, says it's 2 times 2 times 2 times 3, because that's what 2 cubed is. For 24, which is a cube root of 96, I just don't do cube roots well without prime factor trees. So I'm going to do a prime factor tree for 96 and reduce the cube root of 96 using the prime factor tree. And I'm going to cheat and do the prime factor tree on my calculator, which I encourage you to do for your homework. So 96, its prime factoring is 2 times 2 times 2 times 2 times 2, 5 2s and a 3. To do this without my calculator, I could go like 96 is 2 times 48. 48 is 2 times 24. 24 is 2 times 12. 12 is 2 times 6. 6 is 2 times 3. And I'd get the 1, 2, 3, 4, 5 2s and a 3. This is a cube root, so every time I get 3 of a kind, I get 1 out front. Anything that's not part of a 3 of a kind goes under and it gets multiplied. So for the cube root of 96, I have a 3 of a kind. I get a 2 out front. Technically, under I get a 2 times 2 times 3, the things that weren't part of a 3 of a kind. I'm just going to multiply those up. And my answer for 24 is going to be 2 times the cube root of 12, if I did that right. I couldn't do this on my calculator. On my calculator, if I do the cube root of 96, it's dumb and it gives me a decimal. But this decimal, 4.5788567, that would be the same as if I did this 2 shift cube root of 12. You get exactly this number back. Not that that number is even readable, but I could kind of check to see that my answer is right. I can get this out decimal on my calculator, do a decimal for this on my calculator. These have to equal each other if my answer is right. So let's do 25 together. If you're clever, you might be able to find the biggest perfect cube that divides evenly into 500. I feel like it's 125, but I'm not going to be clever. This is just too much work for me. So I'm going to do a prime factor tree for 500. 500 is 2 times 250. It's 10 times 50. Prime factor trees are a nuisance to do by hand. 10 is 2 times 5. 50 is 5 times 10. 10 is 2 times 5. So the prime factoring for 500 is 2 times 2 times 5 times 5 times 5. Again, way better to just invest in this calculator. It says it's 2 2s and 3 5s. In order to reduce this, because it's a cube root, anytime I get a 3 of a kind, I get one of those out front. So I get 1 5 out front, and then the parts that aren't 3 of a kind go under the radical and they get multiplied. This is going to reduce to 5 times the cube root of 4. The clever way to reduce it, if you want to break it up into 2 radicals, I could say the cube root of 500 is going to be the cube root of 125 times the cube root of 4, because 125 times 4 is 500, and 125 is the biggest perfect cube that divides into 500. It just seems silly to do this breaking up for anything that gets, the numbers get big. I just do prime factor trees. They're way easier for me to do. 27 wants me to do 3 times the 4th root of 96. I'll save that for you. And 28 wants me to do 5 times the 4th root of 486. The nice thing about the prime factor tree approach is it's just logical. When I'm doing a reduction of a 4th root, I need 4 of a kind. Anything that's less than a 4 of a kind is going to go under. So I'm going to do a prime factor tree for 486. No way I want to do that by hand. So 486, the prime factoring for it is 2 times 3 times 3 times 3 times 3 times 3. 2 times 5, 3s. And in a 4th root, you need 4 of a kind, and every time you get a 4 of a kind, you get one of those out front, and anything that's not part of a 4 of a kind gets put under and gets multiplied. In this problem, there's a 5 out front from the given problem. I'm going to bring a 3 out front from the 4 of a kind, and under my radical, I'm going to get a 6 from the 2 and the 3 that were left over. And then for an answer for problem 28, I'm going to say this is 15 times the 4th root of 6. Can't really check this per se, other than I can do this. I can go 5 times the 4th root of 486, which is the initial problem, and that gives me 23.476267, and then take my answer, 15 times the 4th root of 6. And if I get the same decimal, if that decimal is equal to that decimal, then I've reduced properly. I guess we're going to have to do a part 3 to this video. Kind of is what it is. I'm going to pause the video and start a part 3 up here in a second, and that will definitely be the last part.